Dear Mathagony Aunt, I have a problem with vectors. There's so little about them in the curriculum and in the exam specifications that it's really difficult to make them come alive for my pupils. Can you help? Isabel Skinner.
Vectors aren't easy, not until you understand them. It's really important that you do real-life applications with your students. It doesn't just make it interesting, but it also helps their conceptual understanding. Remember, vectors have both magnitude and direction. They're a displacement. The simplest example is if I go from here in this direction to here, and then in this direction to here, which in vector terms is the same as going from here to here along the third side of the triangle.
So for you, Isabel, I visited Coombe Dean School in Plymouth. Here, my friend and maths teacher, Heather Rennick, was trying out some practical activities with her class of higher tier Year 10s, which you could try for yourself.
That's it. OK, Josh, you're up next. What I'd like you to do now, from Natalie's beanbag, I'd like you to measure out a distance across.
Their first classroom activity was to lay out two sides of a right-angled vector triangle and then to measure the resultant vector, the direct route.
So what made you start in the way that you did this morning with them?
Well, I wanted to go right back to first principles. And so the idea was that we started off completely at the beginning with the vectors, building up this idea of a journey, of a movement, of a translation that students could do practically, so that the students could actually take their beanbag, measure to another point, so that they could actually see that what they were dealing with was a distance across that was the resultant movement after the two separate movements. OK, you're going to need to flip it over because you're currently in feet there and you want to be in centimetres and metres. It also brought in the fact that they haven't actually done a lot of measuring since probably a way back in their learning. And they needed to remember how to work accurately with rulers and with tape measures.
That's 5 metres 50.
3 metres and 55 centimetres. 3 metres 95.
It's 4 metres 9.
410.
The next part of the activity is to do a scale drawing. You've measured it out on the floor. We're going to turn your measurements into a scale drawing that you're going to do on your graph paper.
The next activity your pupils could try, Isabel, is to draw the same triangular routes to scale and measure the resultant vector.
You've measured the hypotenuse, and what did you find?
Well, if we did, it's 8.5 centimetres. If we put it back into scale, it's 4.25 metres. Well, I would have thought we can be more accurate with a ruler and a pencil than we can on the floor, so we may get some error data. OK. Which important factor about this triangle do you think might have been missing off the floor? The perfect right angle.
The perfect right angle. Well done. It was quite interesting how they would start off with one scale and then realise that if they gradually built their diagram more accurately, but because of the scale larger, that they got a better, more accurate answer at the end. More accurate. OK, so if you wanted to make this more accurate again, what would you do?
Make it bigger.
Make it bigger again. OK, until, I suppose, you could take it up to the size.
The size that it was on the floor.
This exercise also flushed out a problem, understanding scales.
Okay, Josh, can you let me have your length, please, in metres?
Yeah, we used a 2 centimetres to 1 metre scale.
Yeah.
And our result was 8 metres and 20 centimetres.
Are you sure it was 8 metres and 20 centimetres?
Divided by 2.
OK, it was 4 centimetres, 4 metres and 10 centimetres.
OK, fantastic. 4 metres and 10 centimetres. Wow, that was quite accurate compared to your measurement. Well done.
Finally, you can calculate the length of the resultant vector using Pythagoras on the right-angled triangles.
The one I'm doing at the moment was 3 by 3. So I'm doing 3 squared by 3 plus 3 squared, which is 9 plus 9, which is 18. So now the square root of 18 is 4.242.
We've gone through the process of measuring out our vectors, And we found that the most accurate way of being able to measure that was not actually to measure it, but was actually to calculate it. What I'd like to do now is to introduce
Your next step, Isabel, might be to introduce some of the vector notation.
What about the journey that we take between the two?
Right 4 and up 2.
Okay, right 4 and up 2. So 4, 2, I'm going to show you that we write that as a column vector. 4, 2. Now the reason that they are positive is because we're moving to the right and we're moving up. What if we were to go in the other direction? Alex?
Down 2 and left 4.
So this time we're going -4 and -2. That will map us back to our original location.
Then you could let your pupils explore some interactive vector software, which would reinforce some of the abstract concepts involved in vector notation.
That was just a bit larger over there. Yeah. If you know what I mean. Just switch the A and B around. So I think that would be like, because that's 3 down and B at 6 4. Yep. Now put A at 4 5 and then B at 6 2. So with 6 along, just move it down a bit more. So it'll be -3, 2 -3.
How important is it to follow that up with some kind of interactive software activity?
Yeah, I think that we have to take into account the way in which students learn, and one thing that they encounter more and more now is the fact that they want to see something that can be set up really quickly, as by the software that we were using, so that they can actually take a point, move it around and actually see the effect of it straight away, and to be able to do that with lots and lots and lots of examples so that they can see that it has the same effect each time. Though they had a laptop each, they were able to sort of, well, what are you doing? And did you get that? And it's to bring conversation, dialogue and discussion at the forefront of the learning, as opposed to sort of using the texts and lots of questions to get there.
Vectors have both magnitude and direction and can be used to represent velocities, which is really speed in a particular direction. Imagine my hovercraft is travelling at 5 metres per second. And there's a 3 metre per second crosswind. Which direction do you think the hovercraft will travel, and how fast will it go?
It's difficult to see that the hovercraft is actually being blown off course at a slight angle across the river. So we need a vector diagram of what's happening. The 2 component velocities of the hovercraft are 5 metres per second across the river and 3 metres per second along the river.
Unlike walking from here to here and then to there, the 2 velocities are bearing on the hovercraft all the time. The effect in vector terms is as if the 2 velocities are applied one after the other.
Like this, with the resultant velocity becoming the third side of the right angle vector triangle. As messing about with boats is difficult, they set up a similar scenario in the classroom, with 2 electric fans blowing at right angles, sending the ball off in some intermediate direction.
What I was trying to do with the wind machine was to show something that you can't see from a textbook situation. So if you're looking at a situation as we have here with a boat crossing a river, what I wanted to try to do was to show that movement using the wind machine, without having to say, here's a triangle drawn for you already in a textbook. Let's look at this practical situation, and then can we break down that situation back to this type of question?
It's difficult to measure the resultant velocity in the real situation, so accurate drawings and calculations are all the more important. The resultant velocity of the hovercraft is the hypotenuse of the triangle, which you can measure or work out by Pythagoras. And trig ratios will give you the actual direction the boat goes in. So my hovercraft is actually travelling at 5.8 metres per second at an angle of 31 degrees across the river.
There are all kinds of questions you can ask about boats crossing rivers, aeroplanes being blown off course. You could try how far downstream you end up, and at what angle upstream you have to steer to make sure you hit in the right place. vectors also represent forces. I'm hanging from these two ropes and my weight is pulling me downwards. The tension in these two ropes is holding me up. But the ropes are at an angle. So how do we calculate the actual tension in each of these ropes?
Okay.
In the classroom, they had a similar setup, with two pupils pulling against a third, with Newton meters in each string so that they could measure the forces involved, and then see how the forces increased when they increased the angle between them.
Stop.
There we go. That's it.
That's perfect. Okay, Dom, take your reading.
15.
This is not a piece of equipment that we have hanging around in the maths department, but it is something that they've got over in the science department. And what they tried to do is, in discussion with me, we were looking at this idea of the forces and the balancing of forces. And this piece of kit is able to measure the forces in newtons, and we were able to try out some of these questions in a practical way using the Newton meters. Charlie, you need to be there. You need to hold it right there at 120 degrees there. And Teresa, you need to just hold it bang on. Okay, Dom, grab your readings.
19 and 19.
Okay. Right, now you're going to have to try and get a little bit wider again.
30 still.
Okay.
25 and 25.
Because with this type of question, you really can't see a triangle in the question, but you can see the effect of the forces. So you're completely bringing to life the practical nature of the question without having to say, I've got to draw a diagram or I've got to be able to just do it in this way. You can actually see it so much more practically. And the students loved it.
This is the force diagram for the pupils' experiment, with two forces pulling against a third, with the resultant of the two forces being equal and opposite to the third force. With balanced forces, where nothing actually moves, only by looking at the vector triangular forces do you get a clear picture of what's going on. As the angle between the strings increases, you can see on the vector diagram how the tension in each string increases to maintain the same resultant force. And as these aren't right-angled triangles, the sine rule will give you the actual forces involved.
So what, Heather, were the difficulties, the challenges and the excitements of what we've been doing today?
I think one of the things that I found teaching this material is that if you look at it from the perspective of the methods of assessment, you can end up with some very dry, boring lessons. And actually at the end of it, the students don't particularly understand the application of what they're actually doing.
Is that something that happens a lot with higher level students, do you think?
Higher level students, I think, have very often gone through quite a number of years of maths lessons that are very textbook based. And I think what we've tried to do in this activity is to try to bring in lots of practical activities to try to cement their understanding of real applications instead. And I would certainly say to people that were considering bringing in practical elements within the classroom that it is achievable to do. You do have to plan, you do have to research, but you learn something out of it at the end, and so do the students.
So Isabel, I hope the activities you've seen have given you some ideas to help bring vectors alive for your pupils.